This is not a modern oscilloscope. There is no sampling, there is no memory, and there is no triggering. But what you are looking at is a beam of electrons being physically steered through space by voltage. This is a cathode ray tube oscilloscope built from scratch. The cathode ray tube didn't begin as an instrument. It began as a physics experiment. In the late 1800s, researchers like Plucke, Crookes, and J.J. Thomson were studying what came to be called cathode rays, beams of charged particles moving through a vacuum. By 1897, Thomson had shown these were electrons. That same year, Ferdinand Braun built one of the first cathode ray tubes used as a display, a phosphor screen struck by an electron beam. It wasn't yet an oscilloscope, but it established the idea that electrical phenomena could be made visible. Soon after, engineers began adapting these tubes to study waveforms. Early displays were dim, so signals were often recorded photographically with long exposure times. But the principle was already there, voltage controlling the motion of an electron beam. The tube used here, a small electrostatic deflection CRT, like the 2AP1, sits very close to those early devices. Instead of magnetic deflection like later television tubes, it uses electrical fields between plates to steer the beam directly. So, while modern oscilloscopes are digital and abstracted, this is much closer to the original idea. A beam of electrons, controlled by voltage, making electricity visible. This oscilloscope follows a simple structure: the cathode ray tube itself, deflection amplifiers, and a high voltage power supply. The CRT is a 2AP1A, a 2-inch electrostatic tube with a green phosphor. There also exists the 2BP1, which allows for higher voltages and greater sensitivity, and has a longer persistence on screen, but the 2AP1 is entirely sufficient for our purposes. Because of the high voltages involved in this build, several hundred volts throughout, this must be built as a permanent, properly insulated device, and is not meant for the breadboard. Functionally, this is not a modern oscilloscope. There's no triggered sweep, no calibrated time base. It is a direct display of voltage as motion. The CRT consists of three main parts: the electron gun, deflecting plates, and a luminescent screen. Electrons are emitted from a thermionic cathode and accelerated by high voltage. Beyond that are the accelerating and focusing electrodes, often called the anodes. The focusing electrode forms an electrostatic lens. By adjusting its voltage, typically somewhere between 140 and 300 volts, the beam is brought to a sharp point on the screen. This adjustment has been brought out to a potentiometer called focus. The final anode accelerates the electrons forward. In this build, that accelerating potential is about 710 volts. The voltage sets the energy of the electrons, and therefore their speed. At these voltages, they're moving at several percent of the speed of light. After acceleration, the beam passes between two pairs of deflection plates. Each pair controls one axis. A voltage difference between the plates creates an electric field. That field applies a force to the electrons, pushing them sideways as they travel forward. From the geometry of this tube, the final deflection on the screen depends on a ratio: the deflection voltage divided by the accelerating voltage. In practice, this is expressed as a sensitivity, how many millimeters the beam moves per volt across the plates. In this build, applying about 145 volts peak to peak produced a deflection of roughly 33 millimeters. So the system sensitivity is about 0.23 millimeters per volt. The datasheet gives similar values, depending on which plate pair is used and the operating voltage. What matters is not the voltage of one plate relative to ground, but the difference between the two plates. If both plates are equal, there is no electric field, and the beam doesn't move. That's exactly what the centering controls are doing. They're introducing a small DC imbalance, shifting the beam to the desired position. An important consequence of the physics is that the sensitivity is inversely proportional to accelerating voltage. Because this tube is running at about 710 volts instead of the nominal 1000 volts, the electrons are moving slightly slower. Therefore, the beam is easier to deflect. To move the beam across the full screen, about 44 millimeters, requires on the order of a couple hundred volts across the plates. This is why the deflection amplifiers must operate at a relatively high voltage. So the entire system reduces to a few relationships: Temperature releases electrons, voltages accelerates them, electric fields deflect them, and the result is motion made visible on the screen. Aesthetically, I sought to evoke the 1893 World's Fair by adding lightning bolts and various geometric shapes that I felt appropriate. I also worked with the name of the device and put it on a little placard, but now I realize the persistence of the tube I have chosen does not allow my original intent of emulating an oscillograph. I had planned on using my Canon AE1 program, film camera, and adapting the 3D printed collar around the tube into a photographic setup and taking a long exposure shot of the long persistence trace draw. But given I can see in real time the relationships of two signals, it is now more accurately deemed an oscilloscope. I do, however, have the long persistence tube, but it will take other circuit adjustments to use it. So for now, I will keep the circuit as is and live with the placard. I do, however, like the subtext, "A window into the world of tomorrow," as that is exactly what this would have been in 1893. I very much enjoy the nascent age of various technologies. There's so much to learn when you get to the root of a thing, and then you realize it goes even deeper than that, which allows for endless hours of good fun. I appreciate your time in checking out this build, and I hope to see you in the next video.